Thanks. First of all, thanks to the organizer for giving me the chance to do this talk. I'm going to talk about chemical complexity in outer galaxy star-forming regions. So I'm going to start by talking about the outer galaxy, which is a subsolar metallicity environment. And then I will present the results of the project CHEMOUT, which stands for Chemical Complexity in Star-Forming Regions of the Outer Galaxy. And finally, I will give some implications derived from the first results and some conclusions, what we can do from now on, let's say. First, I would like to talk a little bit about the importance of chemical complexity in star-forming regions, because as anticipated by some of the other speakers, the star formation process is a complex process studied mostly from an empirical point of view so far, which implies a change, even very dramatic and quick change in physical conditions. The star formation starts from the collapse of some condensations inside a large molecular cloud, followed by the protostellar phase in which the protostar keeps on accreting and contracting and increasing the temperature. And here there are collapse and contraction at work, and also the production of outflows and shocks. Then the protostar forms a pre-main sequence star surrounded by a residual protoplanetary disk that the system evolves towards a main sequence star associated with a planetary system and everything else that is formed from a protoplanetary disk, asteroids, comets, and so on. The process involves, as I said, big changes in the physics, and that goes hand in hand with a change in chemistry. So physics and chemistry change together, and we matter about the chemical complexity because chemistry can be used to study the physics. There are some chemical species that are very important because very selective of specific physical processes, for example, outflows, inflow, and so on. And then there is also another reason why we study the chemical composition, because according to the so-called exogenous origin of life, the theory of the exogenous origin of life, the organic matter that is created in the early phases of star formation. We now know that there are a lot of complex molecules, complex organic molecules forming during the protostellar stage, are inherited, at least partly, during the formation of the disk, and then maybe also the formation of planets and asteroids and comets. And therefore, the budget of organic matter that was on the primordial Earth could have been due to the presence of organic material on comets and asteroids that run onto the primordial Earth during this event called the Late Heavy Bombardment, when the primordial Earth was bombarded by comets and asteroids, releasing the budget of organic matter and everything else. So, having knowledge of which complex organic molecules and prebiotic species can be formed and preserved from the early to the late phases of star formation is essential to understand the emergence of life on Earth also, and maybe elsewhere in the universe. But so far, this search was limited to the local and inner galaxy, where the conditions are supposed to be very close to that of the protosun. Maybe, this is debated. The outer galaxy, so the portion of the galactic disk that is beyond the solar circle, is a portion of the galaxy that is intrinsically different from the local one. So if the sun is located about 8 kiloparsecs from the galactic center, the outer galaxy in volume represents the largest portion of the galactic disk. But it contains less stars and less molecular gas because stars and molecular gas the density of both decreases with the galactocentric distance. And it is a place where metallicity is subsolar and decreasing with the distance from the center according to the abundances, the elemental abundances measured from stars or H2 regions of carbon, oxygen, and nitrogen. So all of these elements, the most abundant elements after hydrogen and helium, decrease with the galactocentric distance. Not only these elements have a lower abundance, but also their ratio is supposed to be different from the inner to the outer galaxy because the elemental gradients do not have the same slope. So, for example, the carbon decreases in a steeper way than oxygen, so that the carbon over oxygen ratio decreases from the inner to the outer galaxy. The same is true for the nitrogen over oxygen ratio. And therefore, apart from a general decrease of the basic ingredients of molecules, and based on that, we thought that the chemistry was less complex in the outer galaxy. Also, the relative ratios between species was supposed to be different because of this change in carbon over oxygen and nitrogen over oxygen ratio, and which is actually the carbon over oxygen in particular, a very, very essential parameter in regulating the relative ratio of some species. But I am an observer, so I believe what I see, of what I can derive from what I see. And the reality is that maybe the outer galaxy is not as poor in chemical complexity as we thought. There are now several observational results that indicate a complexity higher than expected. One, it's not the only one, but it is one of the most representative results, was the detection of a hot molecular core at the periphery of our galaxy by the group of Shimonishi and collaborators at 19 kiloparsecs. They discovered a hot molecular core, so a star-forming core, forming probably a high-mass star, very rich in complex organic molecules. Actually, this is one piece of the spectrum obtained with ALMA of this region, where you can see in blue many lines due to complex organic molecules, dimethyl ether, methylformate, and so on. And like in local hot cores, local galaxy hot cores, these complex organic molecules come from the central part of the core. So this suggests that the chemical richness and the mechanism by which this chemical complexity is triggered is similar also in this subsolar metallicity environment. So to make pushed by these intriguing results and also puzzling results, and to make this search a bit more systematic, we have undertaken, mostly with a RAM 30-meter telescope, but not only, a project called ChemOut, that stands for Chemical Complexity in the Outer Galaxy, which aims at studying the chemical composition of 35 regions in the outer galaxy, represented by the green points, first in selected spectral windows and then in specific spectral windows. This is the list of my collaborators. In green, you can see the people that is mostly involved in observations and data reduction and analysis. In blue, the modelers, theoreticians for the chemical modeling and chemical theoretical interpretation, including a little bit also comparison with machine learning techniques. I will show you later that. And then I wanted to mention in particular two students, Diego Gigli and Fabio Spaccino, both from the University of Florence, whose thesis is focused on specific aspects of ChemOut, but they gave a very important contribution. So the main goal, as I said, is to study how chemical complexity changes with the distance from the galactic center. The method is the observation of rotational transitions of molecules, in particular tracers of the physics, temperature, density, cosmic rays, ionization rates, and organic prebiotic species. in star-forming regions of the outer galaxy and model their abundances. The target sources are 35 cores with a galactocentric distance in between 12 and 24 kiloparsecs, more or less. They all were detected previously in formaldehyde. So to be sure, let's say, to have at least a significant, an important, even if simple, organic species. The telescopes used so far are the IRAM 30-meter telescope, but we have also obtained data with ALMA, NOEMA, under reduction and analysis, and the JEBES. And in particular, I wanted to mention the contribution of these two guys, Laura Colzi, PI, together with me, of the project, NOEMA project Morgan, molecules in the outer galaxy with NOEMA interferometer, and Alvaro Sanchez, PI of survey complementary to the one that we have undertaken with the IRAM 30-meter telescope with the JEBES at lower frequency. So I'm going to show you quickly some significant results of the papers, the series of papers that we have published. First, just to show you where the sources are located in the galactic disk. As I've told you, they are all in the outer galaxy, in the third and the fourth quadrant, mostly. There is also one object that is very close to the solar circle to have at least one star-forming region observed exactly in the same way like the others, but with conditions close to solar, let's say. And the farthest away object, which is located in the direction of the anti-center of the galaxy, which is at 23.5 kiloparsecs, and it is the subject of a work performed at higher angular resolution. In the first work, we have targeted the most easier to detect, the species easiest to detect, so HCN, HCO+, C3H2, but also molecules containing silicon and sulfur, SO, SiO, and so on, both in the main isotopologues and in some cases also in less abundant isotopologues, and obtained a good detection rate in the usual suspects, so HCN and HCO+, but also a very high detection rate, higher than expected, in the carbon-rich molecule C3H2. And also we have detected a deuterated species, species containing 13 carbon and 15 nitrogen, which are important to study nucleosynthesis of these elements, as I will show you later a bit more. One of the things that we wanted to understand is how the abundances of these species vary, if they vary, and how with the distance from the galactic center, according to the idea that the elemental gradients also decrease with that. But the first setup that we have used, and the first molecules that we have detected, were not optimized for COMS. So one important piece of the puzzle is the presence of complex organic molecules. And so we have observed in a second moment the 15, yes, brightest targets in a setup optimized for detecting methanol. And all of them, all the 15 targets, were detected in multiple methanol lines. So a successful detection, and from these multiple lines we also could derive good estimates of the excitation temperature of methanol, and from these good estimate of the column densities. And this excitation temperature could be used also to derive the column densities of other species for which we had only one transition, so we had to assume the excitation temperature to derive the column density. And in a work that was following this one, led by Diego Gigli, we have derived the column densities and the molecular abundances of all the species available, and plotted these abundances as a function of the galactocentric distance. So, to make a long story short, the different points indicate the observed abundances with respect to H2. The colors indicate two different methods with which we have derived these abundances. So one of the most important assumption in the approach is the derivation of the column density of H2 to derive the abundances, right? So we have derived the column density of H2 starting from the emission of dust, but then converted the emission of dust into emission of H2, assuming a gas-to-dust ratio, which is a crucial assumption, as you can imagine. We have first assumed a constant gas-to-dust ratio, as if it is the canonical value of 100, and the results obtained with this assumption are the cyan points, and the cyan line is the fit to this data, and derived in a second moment abundances assuming an increasing gas-to-dust ratio with the increasing galactocentric distance, according to the trend found by Giannetti and collaborators in 2017. And in this case, deriving the abundance with this different abundance ratio, we obtain a decrease in abundance for all the species analyzed. But if you look at the fit, the blue line, which is the best fit, and you can see maybe an underlying black line, the black line is the elemental abundance of carbon. Here is overlapping. Here, for example, they are separate. This is the elemental abundance of carbon. This is the fit to the abundance of H13CO+. So you see, and there is also the abundance of oxygen that is plotted in red. And you see that even in the second approach, the abundance is decreased, but never more than the elemental abundance of carbon. So in practice, at most, the elemental abundances, the molecular abundances decrease as the abundance of the parent element. So they scale with metallicity, despite maybe other differences in the physics. And another application that we can do with the data of came out is, as I've anticipated to you, the study of the nucleosynthesis origin of some elements, in particular of nitrogen. We have detected in CheMout the HCN and HNC molecules, also in the less abundant isotopologues containing 15N. And by comparing, therefore, the column densities of these two species, we have derived a ratio between the 14N, the 14 nitrogen, and the 15 nitrogen. Nitrogen exists in the form of two stable isotopes, the 14N and the 15N, but the two isotopes do not have the same nucleosynthesis origin. And actually, by plotting this ratio as a function of the galactocentric distance, we can see that there are differences between the inner and the outer galaxy. So the plot here show the points, the measured points in the inner galaxy, which are much more abundant, and the detections, less numerous detections, but still a good number of detections in the outer galaxy in blue. Basically, despite the dispersion, the best fit to the inner galaxy only star-forming regions would be something that tends to increase. But if you include the other galaxy points, it's something that tends to flatten. And this can be explained only if the origin of the 15 nitrogen is dominated by novae outbursts. In this case, you can reproduce this kind of increasing trend in the inner galaxy and then decreasing trend in the outer galaxy. There is a point here that seems to be an outlier, but actually is not an outlier, because when using a distance, the first distance that we had in our hand for this object. It was a very distant object, close to 20 kiloparsecs, but an updated distance calculated from the Maser parallax measurements places this object at much closer distance, where actually there should be the bump of this trend. And finally, if I have time, I don't know, no, 2 minutes? Okay, just very briefly, I wanted to show, the main results of the work that we have performed with ALMA at high angular resolution towards the source that is the farthest away, located at 23.4 kiloparsecs, WB 89 minus 60, 70, something, which is an intriguing object because it's very complex. It's part of a very complex filament. The target of our observation is in the middle of this filament that contains some infrared bright protostellar objects, and around these two protostellar objects, there is a huge chemical complexity and chemical diversity, in the sense that different molecules seem to come from different regions. So just to make it very briefly, we have decomposed this region into 7 subregions according to the emission of the different molecules, and tried to fit with a machine learning technique, starting from a very large grid of models with very large variation of parameters, temperature, density, cosmic ray ionization rate, carbon, oxygen abundance, those that best reproduces the measured column density ratios. And the plots that you see to the right indicate the density probability of the different models that best match the observations. So we have found that the density must be in the range 10 to the 3, 10 to the 3.5 particles per cubic centimeter. The temperature is constrained in between 20 and 40 Kelvin. The cosmic ray ionization rate is not constrained at all, indicating that the species that we have observed are not sufficient to constrain that parameter. But the most important result probably is that the carbon elemental abundance must be basically above 0.2 times the solar metallicity abundance of carbon. And this is totally inconsistent with what should be the abundance of carbon at that galactocentric distance, extrapolating the elemental trends, because it should be 1/14 of the solar one. So this region is rich in carbon, anomalously rich in carbon for the position it has in the galaxy. So in summary, we have found so far that the molecular abundances of the species studied scale at most with metallicity, indicating that starting from a lower amount of material, you can form the same molecules with the same efficiency. The 14N/15N elemental abundance ratio trend with the galactocentric distance is consistent with the models of galactic chemical evolution, in which the 15 nitrogen comes from novae, and the ALMA maps of organic molecules at 23 kiloparsecs suggest low radiation that I have just skipped when talking about the best fitting parameters, and a high, anomalously high abundance of carbon, which was something not expected. Of course, we are now in a process of studying more aspects of chemistry and physics, the cosmic ray ionization rate, for example, and many others. And thank you for your attention. If you have questions.
Thank you, Francesco, for your very interesting talk. I think we have a question online.
So I'm reading for you, Annie. This is from Annie Zabaino, and she said how the molecular complexity as a function of the distance to the center of the galaxy will change the physical processes. So you spoke a lot about chemistry, but it's about physics. So ionization, expansion of H2 region, star formation process, any idea?
So the question is how chemistry would change the process of star formation? No.
physics
could change.
agents, for example,
Well, yes, it's a good question in a sense that there is not only metallicity that is different in the other galaxy, there is less extinction, for example. The density, the column density of material is lower, so there is more exposition to UV radiation. There could be, on the other hand, a lower amount of cosmic rays from the sources of cosmic rays in the galaxy. So I don't know, because I think that nobody knows exactly if there is a change in the mechanism of star formation, but we are studying the chemical composition also for this, so to better constrain the physics. Having knowledge, for example, if really the amount of cosmic rays of UV illumination is compellable or not is a crucial parameter that you can derive from observation of molecules.